Vallahi ben siz yapıyorsun. Şimdi kaydı da ben yapayım hadi.
Hocam daha sağlıklı.
Bir arkadaşınız başlamış ama kaydı yapmaya.
Hocam tamam.
Yapsın yani hiç sorun yok ama ben sonra videoyu bulabileyim.
Hocam otomatik olarak yorumlara düşüyor zaten kayıt bittikten sonra, ders bittikten sonra.
Yorumlar. Bunun İngilizcesine benim şu anda İngilizce kullandığım...
Yorum değil.
Comments herhalde hocam.
Message.
Ne dedi bu adam? En son konuşan arkadaş bir daha konuşabilir mi rica etsem?
Hocam yorumlar dediği arkadaşın chatten, yani şu anda bizim mesela arkadaşın hocam günaydın yazdığı yerden bahsediyor.
Ha orada yorumlar var.
O yorumlar değil aslında, yani orada chat, yorum demek istiyor onlara, o chat yani.
Conversation yani.
Aynen. Chatten yani evet.
Ve conservations aynen.
Ulan. Neyse umarım ben bir şekilde bulabilirim. Bakalım hayırlısı. Hadi başlayalım derse. Şöyle. Where the F is that? Presentation mode. Today we're going to talk about the circuit elements, the basic circuit elements. Most of them are really, I mean, the elements we're going to show you are really just the representations of the actual circuit elements. And most of the models we'll be using will be imperfect. That means that the models will not be adequate. I mean, they will be adequate. It will really be just, remove that thing off, so you don't need to see my face. The models we're going to use are not perfect models, but they mostly represents the behavior of the circuit elements we'll be using. That's why I put this saying about the engineering. What we really do is we imperfect but adequate models to solve practical problems. Let's start with the ideal sources. When I'm saying ideal, that means it really doesn't have any corresponding actual thing in the real world. The first one is the ideal voltage source. We assume that it just maintains constant voltage across the terminals. And when I say terminals, let me just put it this way. And between these two, if you say A in here and B in here, I should really be learning how to write anyway. The voltage between B and A will be plus V of S. And the ideal current source is similar. That means that the current passing through this branch will be constant and is equal to I of S. We call these two independent sources. That means that whatever the rest of the circuit does, these guys, I mean this voltage source, keeps the voltage constant between the terminals B and A. And whatever the rest of the circuit does, the branch current in here will be I of S. Most of the time, this is not the case in an actual or in a perfect world. This is the case, but on the actual world, most of the time, this is not what we see. But very close to it anyway. There are also some dependent sources that we will be working on. For the independent sources, we use this round notations. I mean, the circle kind of notations. And the polarity of the voltage is just shown with this plus sign on one side and minus sign on this other one. I mean, the polarity between A and B, as compared to the voltage between B and A, will be the minus sign of that. And the current passing through this component, this branch through this direction, that red arrow I just draw, will be minus A of S. Anyway, for the dependent sources, we use the rectangle kind of representations. There are two kind of dependent sources, basically. One is the voltage source, dependent voltage source. The other is, that is this one. And the other is the dependent current source, that is this one. It's just the voltage across these two terminals. Let me just put it A and B this time by this manner. Sorry for my bad writing. I'm not used to write. I'm not used to write using a mouse. The voltage across these two terminals will be a multiplicand of a voltage. Just a second. I gotta get rid of that. Just a multiplicand of the a voltage across V of X. Any component across the circuitry, or I of x, the current passing through any branch in the circuit. Similar to that, the current passing through this branch towards this direction, where the arrow shows, will be a multiplicand of a voltage or a current and the circuit is using on. Most of the time we use this kind of representations for modeling transistors, operation amplifiers that we'll be seeing on the 10th or 11th week of the semester. Anyway, yes. Ideal sources are modeled by round elements. Dependent sources, ideal sources, independent sources are modeled by round elements, while the dependent sources are modeled by using the rectangle elements. That's most of the case. Anyway, there are some rules for connecting these elements. I mean, the voltage between in a circuitry, the voltage between A and B going from one branch or the other branch should always be equal. Therefore, if you just do it this way, use this route to come from A to B, the voltage must be equal to the same value if we use this branch. Let me just put one in here and two in here. They should all be equal. If not equal, this representation will not be valid. In this case, this first case, let me put it, the voltage between A and B going from the first branch or the second branch are both same, so this representation is valid. And I mean, you can see that the voltage from A and B from both sides are still same in here, but there is a current source in here saying that the current passing through this branch will always be 5 amps. And it still is valid. I mean, it doesn't come across with anything that we haven't said before. Similar to this one, I mean, this branch, which is series to this branch, should have the same amp, same current, and on both sides. If the voltage sources, the independent voltage source, say something different, then this representation will be invalid. In this slide, all the representations are valid, whereas in this slide, all of them are not. I mean, sorry about this. This was supposed to be in here. The voltage on point from A to B, the potential difference, let me put it that way, on one side is 7 volt and on the other side is 5 volts, so this is not valid. This cannot happen. The voltage, by the way, this B has to be here too. The voltage across the terminals A and B should be equal from this branch with this branch. It's 7 on one side plus 7 on one side, but minus 7 on the other side. So this representation is also invalid. We can say the same thing about the current flowing from the third circuitry. The independent source says it's 7 amps, but same current, this dependent source says it's 5 amps. So this is also invalid. For this one, on the further slides, we'll have something to say. Don't forget about that. Anyway, the same representation, the validity is also available for the independent and dependent kind of combination circuits. Just assume that this is side 1 and this is side 2. The voltage between those two terminals should always be same, whichever the branch you're taking on. As you can see, this one is 10 volts. The voltage from 1 to 2 is equal to V of X on one side, and it is 2 times V of X on the other side. That means that this circuitry is not right. It's simply invalid. Same in here. You see that the current passing from this branch, according to the source, is 2I of X, while according to this branch, it's I of X, which cannot happen. It's just simply not true. So this circuit is invalid. Now, since it's kind of easy, I'm just to say it, can anyone tell me if this first circuit is valid or not? Should I pick a person?
Valid.
That's valid because putting these 2 nodes in here, I'm just one, and let me just say it A and B. writing A and B is kind of difficult, but I'm still doing it. From this blend, it's 10 volts. From the second one, it's 10 volts. So this one is valid. This B1 is kind of very easy. It's also valid. The ampere passing through, the current passing through this branch should be equal to the current passing here. And they're all 5 amps. So this circuit is valid too. How about this one? I know it's kind of easy. Not worth it saying anything. But just valid or invalid? Just give me an answer.
Invalid.
Not valid.
Invalid, that's right. How about this one?
Also invalid.
Also invalid. How about this one?
Valid.
Can happen, yeah. So that's the way it is. See, this kind of connections are very simple. I'm sure even in middle school or high school, they show you something like this in your physics classes. How about this ones where we have dependent sources? This first one is the same as the example we have given. If you just mark these two ends, say 1 and 2, and name them as 1 and 2, the voltage across 1, 2 from both branches should be equal, which doesn't seem to be the way in here. How about this one? That really can happen. I mean, just the voltage you can see is just while measuring this one and this one, they'll both be same. The current passing through this is just will be the triple to that value. Okay, it must still be happening. I'll say okay to this one. Same with this one, but not with this one. Does everybody understand why I'm saying this is not valid? I hope yes. As you can see, the answers, I mean, the current pass coming from this side and this side are supposed to be equal to each other, which is not the case in here. That's why I said that's not valid. Anyway, let's come. Those were kind of just warming up drills. Let's go and just start doing something real now. It's the Ohm's law. Let's try to prepare and just see how it came up to be. It's just the current, as we talked before, is the movement of electrons from one side to the other side of a transmitter. And when the electrons move like this, I mean, they normally shatter around and just hit the surfaces of the media they're just being moved on. So when when electrons move from one side to the other, as this one, due to the scattering around and just electrons hitting each other, you'll be experiencing some kind of a resistance. They kind of resist to it. That's why we call them a resistor. And Ohm's law says the voltage required to move the electrons from one side to the other side of the circuit, having a resistance of R, is the current is calculated by this way. V required to move this much of electrons from one side to the other is calculated using I times R. Vır, as the beautiful Turkish word says, vır. It's the characteristics of I versus V is modeled by just a linear equation like this, and the slope of that equation is 1 over R, which is called the inductance of it. I mean, how do we calculate the resistance of a material? It is really the length of, it depends on the length of the material divided by the cross section of that material and the kind of the material that the kind of the media that the electrons are flowing through. So actually, the resistance can be calculated if this rho is known, that is the resistivity of an element. The resistance can be calculated by just using this formula, rho times L over L, the length of the material, divided by A. A is the cross-section area. The conductance, which is 1 over the resistance, is measured using either ohms, that's kind of strange, or Siemens. Probably all of you know Siemens from some places else. Anyway, it is 1 over the resistance of a material. most of the cases, this is, I mean, we don't really worry about this. Physicists or electrical engineers kind of know how to calculate the resistance of a wire, resistance of a conductor, or sometimes half-conducting materials. Anyway, what we really work on is the Ohm's law. The current passing through a resistive element will produce a voltage, or vice versa. The amount of potential required to move electrons, this much of electrons from this portion to this portion of the circuitry can be calculated using I times R equation. I mean, if the polarity is reversed, okay, you got to be having this minus in here. But the strange thing in here is power is also calculating using the amount of the potential required to move that electrons and the current generated by that moment. And when you just multiply this out, putting V is equal to I times R, you'll obtain the power is I squared times R. Since R cannot be negative, in physics, we don't have negative resistances. And I square is the square of a physical value is always positive. Most of the time, you expect the power to be always positive. But due to this polarity thing, sometimes we'll be calculating minus powers. If the power is positive, we say that the circuit element is using that much of power. If it is minus, we said that the circuit element is producing that much of power. Anyway, for a resistive circuitry, you'll see that it will be observing, it will be using that much of power, and that's why we call resistors as a passive element. I mean, we talked about this on our previous lecture. Does anybody remember that? I know I'm talking to a wall. I'm just really talking to myself in my office. Anyway, let's go and just pretend that you're listening. We can just, using this formula that is I squared times R or V times I, we can calculate the power absorbed by the resistor or the power generated by a voltage or a current source. Take this example. The voltage across this independent voltage supply is said to be 100 volts, and the resistivity of the value of this resistor is 10 ohms. That means the current passing through this branch will be, using the Ohm's law, will be the voltage divided by the resistance. That will be 10 amps. By the way, 10 amps is a huge value. Don't try to grab a wire that 10 amps is passing on. Okay, the power used by the resistor, or in this case, generated by the voltage source, will be V times R, or I squared times R, or V squared divided by R is 1 kilowatts, that is 1000 watts. Now with this circuitry in here, it's said that we have the dependent source giving 5 amps to us. And the resistivity of the resistance of this portion of the circuitry is 10 amps. Similar to that, we can say that power generated or dissipated by the voltage source is V times R, that is I squared times R, or V squared divided by R, will be 250 watts. This one is the power used by the resistor or generated by this current source. Now, what those things we learned correspond in real world? A voltage source is really a battery. Actual batteries are dependent voltage sources, but we sometimes model them as independent voltage sources. A lamp that you use or a bulb you use in your homes can be represented as a resistor. A wire, normally wires have some kind of resistance in here, but if it's a copper wire, we normally ignore that. The conducting pad, we say that it's a conducting pad, doesn't have any resistance at all. These are kind of good things to know, but they're not really just the actual, as we said in the beginning of the lecture, they're not really the actual thing. Anyway, now let's go to the Kirchhoff's or Kirchhoff's. I don't know. I don't know where this guy is from. That's why I'm not sure if I pronounce his last name correctly, but his real name is Gustav Robert Kirchhoff. And he published this rule, the Kirchhoff's current and Kirchhoff's voltage laws, when he was just a student as yourself right now. I mean, really what he said, he put two new definitions to the circuit analysis. One is the node, and the other is the loop or the branch. The node is the point between at least two components in a circuitry. In here, the A is a node because it's a point between the voltage source and the resistor here, similar to the B. B is a point between two resistors, two components, so we can take it as one node. C, yep, it is also a node, but just using the whole section in here, you can just, similar to this one, you can take all this one, just make it a node as for the representation of it, since between at least two components. We have, in this basic circuitry, in the simple circuitry, we have A, B, and C. We have at least three nodes. Now, what Kirchhoff said for his current law, said that for a node, the currents coming into the node is equal to the current coming out from that node. Or you can just say it, currents leaving a node are algebraically opposite in sign to the currents entering the node. That means that the sum of the currents coming into node algebraically is equal to the sum of the currents getting out of that node. In this example, what we say is I1 plus I3 should be equal to I2. Or nodal representation says that I1, I2, the positive current leaving the node, minus the ones that are coming inside to the node, should be sum up to 0. B is the same thing with a different notation in here, saying if you take the currents coming into the node as positive and ones leaving the node as a negative, the sum of them should be equal to 0. C says the same thing. Currents, this is the current leaving the node in our example, and these two are the currents coming into that node. So the summation of them, this portion should be equal to this portion. We also have the Kirchhoff's voltage law, and this is related with a path. That means that anywhere on the circuitry, just assume that this is it. If you start from node A and just complete a whole path, whole loop, the voltages you add up all across this path will be equal to 0. That's called the Kirchhoff's voltage law. Kirchhoff's current law was saying all the currents coming into that node will sum up to the value of the currents leaving to that node. And Kirchhoff's voltage law says if you start from a point and just make a loop in that circuitry, the sum of the voltages will come up to be 0. That's the second one. Both of them really make a lot of sense. But the second one is just if the potential difference between those two is V of S, the potential difference between VA and VA should be 0. Now, for this circuitry, if you start from A and just follow this path I just drawn, you see that minus V of S, I'll come here, plus V of L, plus minus V of C due to the polarity, and plus V of 1 should sum up to 0. That's what Kirchhoff's voltage law says. How is it coming? I got 101 followers, but no answers. That's good. Anyway.
Her şey güzel gidiyor hocam.
Teşekkür ediyorum. Sağ olasın. Thanks for not letting me feel alone Anyway, now using the same sign convention, we can say just assume that we have a node in here. We get just one current coming in, just one current going out. We can just say that these two are just equal. As Kirchhoff's current law can be stated in this way too. Sum of the currents leaving the node is equal to the sum of the currents entering to that node. Similarly, for the voltage case, if you start from one node and just make a loop in the circuitry, when you come to the same point, the sum of the voltages will end up to be zero. Now, using Ohm's law, that was V of an element, the voltage across an element is equal to the current passing through that element multiplied by its resistance. This is what, by the way, is just only valid for resistive elements. We can just calculate this values in here. The VL. VL should be the current passing through that, I of L, multiplied by the resistance in here. Same in here. And same in here. The funny thing is, I of S, we assume just flowing this way, is same of I of L, but have the negative sign with respect to I of C, and is same of with I of 1. Let me try to write it in here. I of S is equal to I of L. Sorry for my bad writing. If it was on a whiteboard, I probably would have written a little bit better than this, but not as good as you expect. It is minus I of C, and that is equal to, oh, I'm getting worse, I of 1. By the way, this is I. Daha üstte yazan. Üst yok bir tanem. Bu var, buraya yazmaya çalışıyoruz. Merak etmeyin, slaytlar şu anda faizla. Slaytlar şu anda şeyde görebilirsiniz. Adı neydi? Bu grubun dosyaları arasında görebilirsiniz. Buraya da koydum. Elimden gelince şeye de koymaya çalışacağım. Moodle'a da koymaya çalışacağım. Anyway, let's continue. Using that relationship, starting from node A, I can just write that the summation of the voltages on that loop will end up to be 0. You can convert it to this one, but it's really unnecessary. And the currents I that I'm just assuming that is passing through this branch over here. We haven't yet introduced meshes. Should all be same. Just writing that over, just using 1 and 2 together, we can say that V of S is equal to I of L multiplied by R of L plus I times R of C plus I, that I is this value in here, times R of 1. Combining them up using some math, we'll be able to calculate V of S using the resistive values, and or calculate I if the V of S is given to us. And that is, I will be just like this. And using this, and this relationship in here, I can calculate every current passing through that element. When that is also done, I can also calculate using the power. What was the power? Power was V times I. Now the voltages are known, currents are calculated. I can calculate all the powers dissipated by all these resistive elements. Now, can is not a good word. Let's just do it. This is our example. You can see this time the values of the independent sources and the current, the resistance of all the elements are given. And we got some notations for V2 is the resistance, the voltage across this 3 ohm resistance. V5 is the voltage across this resistance, and V1 is the voltage across this 2 ohm resistance. First let's try to find I of 5. I of 5 is not that hard. It is, the voltage in here, I of 5 is the current passing through all components in here like this. So just divide the voltage by the summation of these resistances. V1 then can be calculated just multiplying that current with 2, but just don't forget the polarity of it. It will be minus whatever the current is calculated times the resistivity. The resistance, resistivity is kind of different. V2 can also be calculated just multiplying the I by 3. This time polarity is positive. V5 is same, that multiplying the current by the 7 ohm value. And the overall power generated by the voltage source can be calculated by Vs multiplied by I5. And that's a 5. Can you believe that? Anyway, let's see the solution then. For the first one, just use the Kirchhoff's voltage law. I know it's kind of easy, but it's kind of easier for me to explain it this way. The VFS is equal to plus V2 plus V5 minus V prime. That is, this one is 3 times I5, that one is 7 times I5, and that one is, what's that, 2 times I5. Using that equation, you can calculate I5 as 2 amps. Now, since we know I5, we can just calculate V1, just multiplying that by 2. But just mind that minus sign over there. So it's minus 4 volts. Similarly, V2 can be say calculated by multiplying the current by 3. That is 6 volts. Similar for V5, and the power generated by the 24 ohm voltage supply is, just multiply those two together. It is, as you see, it is minus 48 volts. It's minus because it's generated, it's not dissipated. If we were to calculate the powers of the resistive elements, you'll end up with having plus values for the power. Now let's take a second example. This time the example is kind of a little bit different due to the parallel connections of these two resistances in here. I mean, if you just do this loop or use this loop, whichever it is, it should just give you the same values. Anyway, let's, for the first equation, we'll use the KVL plus the Ohm's law. That is, the V of S should be equal to V1 plus VR1. By the way, VR1 and VR2 should be equal to each other as they are connected in parallel. I mean, the voltages, the potential between those 2 points have to be equal. So the voltage around R1, the voltage around R2 has to be equal to each other. Anyway, the first one can be calculated by this manner. And the second, if you just make a loop in here, you'll end up something like this. The third one is the current on this loop, on this node, sorry. The current coming in here, it's I, let's call it I. I should be equal to the current leaving to this node. That is, there are 2 currents living in here. First one is I2, the second one is I1. That I is equal to I1 plus I2. Just collecting this, using these 3 equations, we'll be able to calculate the current, I mean, the total current passing through this node in here, then calculate everything else. I just did all the calculations for you. And since this is a kind of an easy circuitry, still, let's go through it. Let's still go through it. Just put the third equation into first one. You'll be able to obtain this value. Now call that 4. Substitute 2 in 4 now. You'll be able to say that, okay, since these 2 values are same, I2 can be calculated using the resistances of those 2 elements multiplied by I1. So if you add them up, you'll end up with something like this. Now 4 changes something like, using 4, now since there's only one current value in here, I'll be able to calculate that value using those resistive values divided by V of S divided by the total resistances, and it will end up to be 5 amps. And due to this relationship, I can also calculate the second current, and it will end up to be 20. And I'll go back and just use the third equation in here to calculate the whole current passing through this first entry in here. It will be just summation of that too. So from that point, everything and every current passing through every branch in the circuitry are known. So we can do the rest and just calculate whatever we want. Now this is kind of a little bit different. The voltage across this branch is given. The total voltage on the voltage supply is given. We don't know the current in here yet, but we are asking what is the value of R in here. The first thing we should be able to notice is, since we know the current passing through here, we know the voltage across that terminals, I can easily calculate I1, which is just 5 amps. And since the same voltage should be also across these two terminals, also calculate I2. Now summing them up, I'll end up with calculating I1 due to the nodal relationship in here. That gives me that the potential difference between these two, what was it, 50 volts, divided by this current will give me the answer, and that is 2 ohms. How are we coming? Okay, I assume that you're following.
Fine hocam.
Now, as I said before, initially, I tried to just warn you about this problem on, 6 or 7 slides before. Normally, when you connect two voltage sources in this manner, it is simply invalid. We cannot do anything like that for ideal independent voltage sources. On an actual world, all voltage sources have some internal resistances in here. So if you just put two voltage sources like this, two batteries having different voltages on them, if you just connect them parallel with each other, you'll see that it works. It's not invalid. That is due to the internal resistivity of each component in here. They normally have, let's assume that the internal resistance of the 7 volt voltage sources are 1 and the 5 volt voltage sources are 2. No, this is the actual circuit when you just connect two batteries together. If you just use KVL, you'll be able to say that the voltage across these two terminals, if we were asked the voltage between these two terminals, it will be +7 -5 times the current passing through these two values multiplied by the summation of those. And if you just do that multiplication, you do that calculations, you'll end up with something like this. And just subtract 5 from 7, you'll end up with 2. Now, that is the current I can easily just calculate if I knew the values of R1 and R2. And for the voltage difference between these two lines, you can say that it is +5, just 5 plus I times R2, or just using the other way around, 7, this time minus due to polarity, times R times R1. Just looking at those two values, can you guess the voltage difference between those two? Can you at least just make a clever guess saying it is between those two values? Assuming I is positive and the resistances are positive, I can say that the value of the voltage across these two terminals should be greater than 5, but less than 7. I hope you understand it. Anyway, if the values are given to us or equal to each other, we can just say that, yeah, we can just find these two equations. And since r's cancel them out in here, it is 7 minus 1 or 5 plus 1, which is just 6 ohms. Normally, this is not the case. The resistivity of different voltage sources are normally not equal to each other. But I mean, it's if you just come up with something like this, that's what you're going to end up with. I'm kind of tired. I want to give a break. How about you?
Olur hocam.
Bir ara veriyoruz beyler. Recording'i durdurun, bir daha record ederiz. Bir 10 dakika sonra buluşalım. Ben kaçtım.